So, hello again. So it's my turn to talk about airtightness in EP calculation, and I will talk more specifically about the European standard EN 16798-7. So, first of all, what is this European standard? Maybe you are not that much familiar with the standard number. So, what you need to know about it is that during the last revision of the PBD, the European Performance of Building Directive, there were a requirement for standardization to develop a full set of standards to actually explain how to calculate energy performance of building. So when it comes to ventilation, this full set of standards has been called the EN 16798 family. So we've got multiple EN 16798. So -1, for example, is about the design of indoor air quality. -3 is about the design of non-residential building. -5 is about the calculation of flow rate in the ventilation system. And -7, the one that I will present here, explain actually how to determine airflow rate in buildings, including infiltration. So here we are in the right standard to know how to take into account airtightness to calculate the energy performance of building. So the objective of this standard is to calculate the air change rate in a building and to include this value in the energy performance calculation. So the problem is that it's not that easy to calculate air change rate in a building because everything depends on everything. The impact of airtightness will depend on the ventilation system you have, on whether you open windows, on whether you have vents, and on how the leakage are distributed along the building, on the wind and everything. So actually the standards propose two methods, which are basically in line with what Nolwenn has presented at the beginning. The method 1, which is about, well, using an equilibrium pressure model to detail precisely airflow rate all around the building. And the method 2, which is about just using simplified calculation by relying on national average. So this is basically a simplified method that Nolwenn has presented. So the standard doesn't give much detail on this method 2. It just say, okay, if you really don't want to use EPM, then you can use this simplified method, but it's for your country to decide what are those national average, basically, of flow rate. But in the standards, we give much detail on how to calculate precise airflow rate. So for the method 1, you will need to use as input detailed characteristics of leakages, air inlet, windows, passive duct, combustion system, and ventilation system. Because as I said, anything that induce a flow rate interact with one another in a building. And then, as an output of the method, you will get the actual airflow through leaks, air inlet, windows, passive duct, combustion system, and ventilation system. So, how does the equilibrium pressure model works? Basically, it's based on the assumption that the mass balance equation, you will have as much flow rate going in that flow rate going out. Okay, the mass flow rate in and out will be the same because the building will not implode or explode. So basically, it needs to be at the equilibrium. So you need to know for every opening in the windows, what is the flow rate through this opening. But this flow rate will depend on the characteristic of the opening, and it will depend also on the pressure indoor and outdoor. So in the end, you will have one big equation, the mass balance equation, with only one unknown variable, which is the internal pressure. And you will calculate what is this internal pressure, so the actual mass balance is 0. You see? So basically, you've got one equation, one unknown variable. The only problem is it's not linear, so you'll need a solver to solve this equation, but it's just one equation, one unknown. But to establish this equation, you need the pressure distribution all across the envelope and the leakage characteristics and airflow path. So the problem is the only thing you have usually is the airtightness value. the airtightness value of the building that you have obtained either through a blower test or a pulse test, for example, no matter what, but you just have this value. And so you need to make a lot of assumptions. The first one is the leakage distribution. Okay, you know in general what is the airtightness of the building, but you actually have no clue where all leaks are and how much they weight in the total balance. So what the standard proposes is first to say, okay, you've got one leak on the roof, just one, and its size is actually proportional to the area of the roof divided by the total area of the envelope. Okay, then you've got the rest of the leaks that are on facades. 1/4 of it is downwind at the top, 1/4 of it is downwind at the bottom, 1/4 upwind at the top, and 1/4 downwind at the bottom. So the first assumption that the standard does is to create a leakage repartition from the measured airtightness, so N50, Q50, Q4, whatever it is. And then it assumes a default value for leakage, which is always the same, which is 0.667. This value can be changed, but that's the default value proposed, and it assumes that all the leaks have the same one. So that's about determining the leakage distribution, first assumption of the standard. The second thing is once you've got the leakage distribution, so you've got those CLE path for each pass basically, you need to know what is the pressure difference between each side of the leak to actually estimate the flow rate. So the pressure difference, obviously that's easy, is the external pressure minus the internal pressure at the leak's level. The external pressure is calculated according to the pressure due to wind here and the pressure due to thermal draft compared to the reference pressure at the floor that is assumed to be 0. And indoor, this is the internal equilibrium pressure minus basically the thermal draft. Okay, it depends on the height of the leak, and the height of the leak is given here. And this is what is the unknown on the first equation of the mass balance that I was talking at the beginning. So this is the one thing you don't know and that you need to solve to get the actual flow rate through leakage. So now the other thing that is not that easy to estimate is the wind speed. So for the wind speeds, usually in files you've got the meteorological wind speed, which is not the wind speed at the leak. It's the wind speed at 10 meters usually that you've got. So you need to convert it to a wind speed at the level of the building. So it will depend on the roughness and the topography around the site and everything. And then you also need what we call the CP coefficient, the pressure coefficient on the facade. So here again, well, the standards provides a default table so that you can use to estimate the CP coefficient, depending on the height of the airflow path on the facade and depending on which facade we are, if it's shielding or not. So this has been taken from basically an AIVC document. This is from the ligament document, so the green one for those who are used to use it. So once you got basically the expression of each flow rate through everything in the building, you calculate the mass balance. So you use a solver, whatever it is, to say, okay, the sum of all those flow rates is equal to 0. What is the internal pressure reference to get a 0 here? And then you can go back to estimate the actual flow rate through leakage. Okay, but what is very important is that it depends on every other opening and on the ventilation system. So basically, if you've got an extract-only ventilation system that will tend to put the building in a negative pressure, you won't have the same impact of leakage than if you have a balanced system that basically provide only a 0 difference in flow rate. So every pressure difference will be due to wind and stack effect. So the more wind, the more pressure difference, the more impact. So it varies all along the year, and the impact of leakages is usually much more important in the winter when you've got more wind and more temperature difference than in the summer. So why this method is more accurate than simplified methods? First of all, it provides dynamic infiltration rate. Usually we calculate on a hourly basis or on 15-minute basis. That depends on regulation. Usually it's 1 hour. It considers real-time factors such as wind speed and direction, indoor and outdoor temperature difference, and it aligns with the methodology for airflow simulation like CONTAM. So this is basically what is in CONTAM. And as Norwen said at the beginning, this method is used at least in France and Czech Republic, to our best knowledge. So the key benefit is that it provides a higher accuracy than simplified infiltration models. It's matched well with measured data, for example, tracer gas methods, because even if we have to make a lot of assumptions regarding the leakage repartition and the actual wind speed, it does actually perform quite well in average. The challenge is that it requires detailed data on building cracks and pressure distribution, and of course it requires a computational calculation. You cannot solve that all by your own because it's a nonlinear equation. Now I wanted just to stress a future challenge for 16798-7. All what I presented here assumes that the building is just one zone, which is okay, that's the first step. But in real life, the building is usually divided into different zones that have opening between them, but may not be, the difference may not be at the exact same pressure. And those pressure drop inside the building will impact also the inlet and outflow, the inflow and outflow. So we would need to include these multi-zone calculations in the 16798-7 to be even more precise in the calculation of flow rate. It's even more important for windows airing, of course, but it also impacts leakages. So yeah, and it would be good to stress in the next standard that we should include simplified calculation both for heating and cooling seasons, because all existing equations that have been done, such as dividing by 20, etc., have been done to be safe side for the heating period, but may not be relevant for the cooling season. So that's also something that would need to be stressed in the 16798-7.